Hello again. Okay, so this time I'll be looking at another example of the infinite square potential. So, different way of looking at it. So in the last case, we had a pretty simple potential where one wall was at the 0 of the x-axis and then one was at L. Right. Yeah. So we're going to look at something different. So we're going to say that potential now is even about x equals 0. So we'll say it's from negative L on 2 to L on 2, and it's infinite outside of this region. I'm going to write this slightly differently. So we use absolute values. So inside this and outside. Right. So again, we'll do the same thing. We remember from here. Remember doing all this, and we find when the potential is infinite, we get that k equals I infinity, and then we find that the wave function at these points in these regions is 0 because of square integrability and all that. Alright, and then again we'll do the same thing for inside the well. We get again the same for k, and again, yet again, we have to use the boundary conditions. So at negative L on 2, that's the same at L on 2, which is 0. So straight away we'll say 0 equals equals a e I k L on 2. That's a 2, not a k. Looks like a k for me. Plus b e minus I k L on 2. Okay. Now what we'll do here is we'll rearrange this. So let's make the b negative. So a equals I k L on 2. That equals negative b e I k L on 2. And then we'll move the exponential to one side, so we get a equals negative b e, and so that actually goes down to the bottom, and that's already actually down on the bottom, so it becomes a negative on this side. That means times each other. You get negative I k L. Okay. And then we can do the same for this boundary condition. Right. Oh, actually, it looks like I did that for the first one. We'll do that for this one now, because I think we had the positive on this side and the negative on that side, so now we'll do it the other way around. And we'll get, I'll just use this, I don't have to write it again. We get negative there, negative, positive. So then what we get then is positive here. So what we can write in general, we'll say in general a, the arbitrary constant a, equals plus or negative here. So negative b e to the plus or negative I k L. Ooh, fancy schmancy. Now what can we do with this also? So we also know that we can split this up into two different equations, and they all both equal a. That means they both equal each other. So negative b e to the, I'll do the negative first, I k L equals negative b e to the positive I k L. Right. So these b's disappear, and the negative signs as well. I'll move that all to one side and we'll get 0 equals EIKL minus E minus IKL. Wow, what do we find? We find something very nice. This is also again this KL. Yes. But we can do something. I'm gonna do something fantastic. We don't have to make an arbitrary constant because we don't have an arbitrary constant. We have constants, magical constants, which will divide both sides by 2i. That means they just disappear. But now we have to find how this becomes 0. We've done this before. We know that then k L equals n pi for n equals 1, 2, 3, 4, 5, 6, 7. Alright, and then rearrange this. K equals n pi on L. So we know that we have then we could say that's a sine n pi x on L, but that's not useful at the moment. I'll clear that away. Bye bye, bye bye, bye bye, bye bye, bye bye. That's not what we want to look at yet. What we want to do then is we can also say, well, look at this. Look at this here. This can go further. What we can say is, remembering the Euler's formula, so E, what am I going to try and do here? E I theta equals, I'll do the general one. A, it's cos theta plus I sine theta. Now this, we know this, when it can be applied to this. So A then equals minus B cosine KL plus or minus from there I sine KL. Ooh. Okay, and we know what K equals. It's n pi on L. So we'll substitute that in. We'll shove it in. Yes. So it's n pi, n pi L on L. Plus or minus I sine n pi L on L. So I'll clear it up here. Those L's disappear. And just like before, we remember that for all integers of n, sine pi, oh, now it's pi instead of 2 pi, but again, remembering the unit circle, so pi is on this side. Every time sine pi, 2 pi, what have I done? Pi, yeah, and then 2 pi, no, this 2 pi is there, and 3 pi, 4 pi, 6 pi, 7 pi, for all the different pi's, it's going to be 0, right? Well, that was slightly confusing, but you get the idea. So, that equals 0. That's going to disappear. Bye-bye. It's gone. It's out ha. And we're left with this. Interesting. So, let's get some space. I need a bigger rubber. Okay. So what did we find then? Okay, I'll write it out again. So A equals minus B cosine n pi. So when n is negative, not negative, when n is odd. So for when, let's go down the next line. This will equal negative b times 1 or negative 1. Negative 1 for n equals 1, 3, 5, and so on. All the odd integers. And it equals negative b. Oh, sorry, that equals then b. cosine will equal 1 for n equals 2, 4, 6, 8, 10, and so on. So it equals negative b for all the even integers. So what's that do for us? Well, if we find out then, I'll clear it again. I have a really small area to work in, don't I? Okay, so we could say, how shall I write this? I'll say a wave function, and I'll write odd for all odd n equals a e okay I k x, and we have it's plus b here, but then we know for all the odd n it's going to equal b will equal a, so we'll say plus a I k x. Oh, why did I write it around that way? Let's do it this way. Yeah, that looks better. And again, by Euler's formula, we'll get that that's equal to 2a cos kx. And we can do the same. Oh, and we'll make that nice, one nice constant. And for even, equals a e I k x, and b equal minus a, or a equal minus b. We'll substitute in for the a, because we like a's, remember? Well, I do. I k x. Again, so I'll call this double prime, because it's a different arbitrary constant. That's the sine kx. Yeah, well, because remember for this is 2ia, and then we made that double prime. Well. So we have now found that we actually get two different equations, wave functions. How crazy! So what we have to do here, then, we have to normalize both of them to be able to get any meaningful information out of either of them. Righto, so I will normalize the odd ones. Yes. Normalize the odd ones. Norm squared. And again, remember the piecewise way, we're only get a meaningful answer where the wave function actually has is non-zero. And so we have what I have for the odd one. It was a prime, wasn't it? A prime. And it's cosine for all odd ones. N by x on L. Yeah. Remembering taking the complex conjugates here. A prime cosine n by x on L again as dx. And then we get take the constants out the front. A prime squared. Oh, I'll also fix that left to right. Did I put a negative there too? How embarrassing. How embarrassing. Anyway, so 0 to L and 2 and times it all by 2, so it's equal in the end. Everyone knows this magic trick. Cos squared n by x on L dx. And then, so that's a prime squared on half when we do the trig thing, but that cancels with that 2 L on 2. Blah blah blah. Actually, I'm just gonna skip ahead here. That's x minus that'll be L on 2n pi and sine 2n pi x on L dx. Oh, what am I doing? I was skipping ahead, wasn't I? 0 to L on 2. Substituting that into here again, that goes to 0, then 0 goes in there, 0. So we're just left with an L on 2, so we find this equals prime, squared, L on 2. And again, so we find I prime equals the square root of 2 on L. Wow, that's just like before. And similarly for the other one, for even, we'll find that A double prime is the same. So, okay. Let's do this. Clear my blackboard. Clearing. Okay. So we'll say that the wave function, we'll do it like this. The wave function has two answers, two functions. So we have the first one, the odd one. Actually, I'll simplify it here. So we have 2 on L times the two wave functions, and one is the cosine and pi x on L, and sine and pi x on L, and that's for all odd, and that's for all even. And wow, wasn't that simple? Well, hopefully you enjoyed that. I certainly did. Bye.